Back to the cosmos. Now we want to talk about formation of planets and eventually, of course, end up with our own planetary system. And the astronomers tell us that if you're going to make planets, the first thing you have to have is a star. So now we know how stars form. So out there and amongst all this cosmic dust that fills the space between the stars, a new star is created. Now, how it's created, I'm not really sure, except one thing I read indicated that perhaps it was the energy from a nearby supernova that resulted in the formation of this new star. So the picture I want you to have then, brand new star forms surrounded by cosmic dust. If you sort of picture this sphere of cosmic dust, then the astronomers tell us that stars, of course, rotate. It seems everything rotates in the universe. And I think that's how it generates the gravitational forces to hold everything together. But the star starts to rotate, and the astronomers tell us that out from every star there's a magnetic field. So picture this magnetic field then sweeping through this sphere, if you will, of cosmic dust. Well, there are things in the cosmic dust that are magnetic, and they're attracted by it, and they start moving along with it, and they get everybody else moving with them. And so picture as time goes on, this sphere of cosmic dust starts to rotate. And remember how the galaxy flattened out when we talked about the rotation of all those stars? The cosmic dust cloud does the same thing, and as a result, eventually you get down to the point where this original sphere of cosmic dust is now a disk of cosmic dust extending out from the equatorial regions of the star. Now, in addition to that, while all that was going on, there was another very important process going on. Coming away from all stars, there's an energy force called the solar wind. Now, this is not wind as you and I think of it. You and I think of wind as moving air. That's not what this is. What this is are high-energy particles coming away from the star. But the interesting thing is that that energy does the same thing that the wind does. Remember the wind, what it does? It picks up light things like pieces of paper and leaves and blows them away and leaves behind heavy things like rocks and stuff like that. Well, in the case of the cosmic dust and this force coming out, the solar wind, it does the same thing within the cosmic dust cloud. It picks up the light things, remember, which now are those frozen ices, okay, and moves them out to the outer edge of this disk, leaving behind closer to the star the heavy materials, the dense materials, the rocks, the minerals, and the metals. And now out toward the outer edge, you still have some rocks and metals out there because they were there in the first place, but most of those ices now have been moved to the outside edge. So picture what you've got now. This disk of cosmic dust has been now segregated by density into the denser things closest to the star, the lightest things, the lower density things furthest from the star. Then what happens? Well, here's another thing I never could quite figure out, but anyway, the astronomers say that within this disk, little eddy currents start to form within the disk. And these eddy currents now, once they start moving, remember Isaac Newton with his gravity force, as things start turning in space, this force of gravity is generated perpendicular to the direction of motion toward the center of rotation. And as a result, these individual eddy currents now, as they start rotating, any cosmic dust within them starts to rotate and collapse toward the center. And so picture now, each of these little disks, each of these little eddy currents within the disk are now collapsing on themselves. The individual pieces of cosmic dust, which I guess are dust size, start to slam into each other, and the particles get bigger and bigger and bigger as this eddy mass collapses, and eventually they turn into what are referred to as planetesimals. Planetesimals are simply sort of odd-shaped pieces. Note, if they're close to the star, they would be made of rocks and minerals and things like that. Further from the star, they would be made of things like the ices, but they start slamming into each other, and eventually, down at the very core of this thing, down at the very core of each one of those eddy currents, there's going to form an object that's going to grow larger and larger as more of those things slam into it, adding to it as time goes on. And eventually, sooner or later, it gets to the point where it takes on a spherical shape. Now, I find this an interesting thing. Apparently in space, you have to have a certain amount of mass before gravity can mold things into a sphere. Think of the moon and Earth, they're all spherical. That's because there's enough mass for gravity to actually do that. There seems to be a certain amount of mass you have to have, a critical mass, if you will, under which the objects will simply be odd-shaped. Well, in this case, sooner or later, down in the center of each one of these little rotating masses, there's going to be a spherical shape form. And whenever that forms, now we have what is called a protoplanet. Now, note again now. In the protoplanets nearest the sun are going to be, or nearest the star, are going to be made of rocks and minerals and things like that. The protoplanets furthest from the star are going to be made of things like ices. Now, this process continues on as the little protoplanets go around the new formed star, sweeping up what remains of the cosmic dust, sweeping up what remains of the planetesimals. They are getting fewer and fewer in number, so the impacts now, the collisions of those things with these central bodies starts to drop off, and eventually they start to get to a size where now the crush of gravity once again is great enough that some of the gravitational energy being turned into heat sounds like the story of a star, but the interior of this thing is not going to get into the millions of degrees this time. We're only talking about getting into temperatures perhaps in maybe 2,000, maybe 3,000 degrees centigrade. But even at that, 3,000 degrees centigrade is high enough to melt any rock we know. So picture then this planetesimal. As things start to melt within it, now we have another density separation taking place within the planetesimal. Whatever happens to be the densest stuff of all is going to settle to the center and form a core. Then surrounding that dense core, layers are going to form, decreasing in density outward until the lightest material, the lowest density stuff, is going to be on the very outside. So now we have a different scenario. We have now a body that has a central core with layers of decreasing density outward. Once you do that now you have a planet. That's the big difference between a planet and a protoplanet. If you were to slice a planetesimal in half, the inside would be totally homogeneous. But if you slice a planet in half, now you see an interior core surrounded by these layerings. So anyway, now we have planets, and there's the big difference. Note the planets closest to the star are going to be dense planets. They're going to be made of rocks and minerals and metals and things like that have an average density of about 6 grams per cubic centimeter. The planets out furthest from the sun or the star are going to be light planets made of frozen ices, densities probably somewhere around 1. If you want an example of that, all you have to do is to look at our own solar system, because our own solar system is a beautiful example. So if you look at our solar system, first of all, let's talk about the cast of characters here. In our solar system, we have one star, which of course is our sun. And note again that it's a rather smallish star. This is a small, lightweight star. Then we have 9 known planets. Now I say known because it always has been thought that beyond our most distant planet that we know of today, there are other planets. We've always thought that. But within the recent years, there are some investigators who say they have found some out there. Now, from what I've read about that, maybe they have, maybe they haven't. But I assume someday they're going to prove that beyond our own solar system, our known one, there are indeed other planets. So there are 9 known planets. Then there are around those planets about 31 plus satellites, moons, if you will. We have 1 moon, Mars has 2 moons. Most of the moons, satellites, are around the outer planets. Now I say 31 plus, that number's going up all the time too. We're sending space vehicles out to those outer planets now, and we're seeing other satellites, smaller ones that we were never able to see before. Now we can see them because we got space vehicles out there taking high-resolution photographs and that. So we have 31 plus of those. Then what we have, let's see, the next one on the list would be the asteroids. The asteroids are these odd-shaped bits and pieces of rock that orbit around the sun. In numbers, they probably, well, they're about, they say 100,000 named or numbered ones. Undoubtedly, there were many, many more than that. Those are the ones we can actually see from Earth with earthbound telescopes. But there are others undoubtedly out there. So there may be millions of those things. And then the next little character would be our meteoroids. Meteoroids are sort of, to me, very mysterious things. They're made up of rocks and iron. The thing about the meteoroids that are different from everybody else is that everybody else seems to be in some kind of an orbit around the sun. Meteoroids aren't like that. They sort of roam through the solar community and don't seem to have any particular path to follow. And then finally we have the strange agent, of course, of the solar system, which are the comets. There are about 100 or so named comets, and again, named, implying that there are others we'll probably discover, and we are discovering more all the time. But these are simply, as we'll find out, just strange balls of frozen gases that are out there, and we'll get around to those. Well, the first thing I'd like to do, I'd like to talk a little bit about some of the inner planets. The inner planets each have something to teach us, mainly about Earth. I'm not going to say an awful lot about the outer planets because I really don't know an awful lot about them, and it seems they really don't have anything to contribute to our understanding of Earth. But let's take the innermost one, Mercury. Mercury, innermost planet closest to the sun, as you would expect, is probably pretty warm, and it is. Noontime on the equator. Noontime on the equator is about 450 degrees centigrade, which is pretty warmish, you have to admit. But midnight on the equator, it falls down, I think, to something like 170 degrees below 0 centigrade. The thing about Mercury is that it has the greatest range of temperatures of any of the planets. And the thing to learn about that, the reason why is because Mercury basically has no atmosphere. Any atmosphere that Mercury ever had has long since been blown away by that solar wind we talked about coming from the sun. What atmospheres do? Planets like ours that have an atmosphere, the atmosphere constantly conducts heat from the sunlit side to the dark side. So the idea is that when the sun goes down around here, obviously it cools off. But one of the reasons why it doesn't cool off any further than it does is because you're constantly conducting heat around from the sunlit side all the time. And the denser the atmosphere, the more heat that you're going to conduct. Possibility of life as we know it on Mercury? I don't think so. Actually, the reason why is interesting. The reason why there is only one and only one absolute requirement of life as we know it, and that, of course, is water. Anywhere you can have water, or do have water, you can have life as we know it. Well, there is no water on Mercury. I think we're pretty safe to say that one. Venus, the next one out. Venus, now here's a planet all of you have seen. Well, if you live in the northern hemisphere, that is. Venus is the brightest star in the northern sky. Now, obviously, it's not a star at all. It's one of our sister planets. And the reason why it's so bright is because it's the planet that's completely surrounded in a thick cloud cover. What you see if you were to view Venus from Earth with a telescope, what you see is not the planet, but you're actually looking at the top of that layer of clouds, that thick layer of clouds. Now, clouds are really good reflectors of heat, of light. Think about driving along on a summer evening and you run into a fog bank, how your lights come back at you. Basically, that's all fog is a low-flying cloud. So they're very good reflectors of light. So that's the reason why Venus is so very, very bright. Now, the interesting thing about Venus, temperatures on Venus, day and night, makes no difference where you are, about 485 degrees centigrade. Now, note that's higher than Mercury, even though it's further away from the sun than Mercury. Why? There has to be some reason. And the reason why, of course, is because of something we call the greenhouse effect. You all know that the greenhouse effect basically is this mechanism whereby the lower reaches of our atmosphere is maintained at a certain temperature due to the presence of greenhouse gases. Now, the greenhouse gas on Earth, it does most of the work, although it's not the best in terms of doing the job. Methane probably is the best doing the job of greenhouse gassing, but carbon dioxide is the one on Earth that does most of the work. Well, anyway, the carbon dioxide content of Earth's atmosphere is such that it is kept at about, 15 degrees centigrade on the average over the long haul of geologic time. Well, it just so turns out that those clouds surrounding Venus are not the kind of things we have here. They're not water like ours, carbon dioxide. The Venusian atmosphere is about 95% carbon dioxide. So it's this super greenhouse effect that results in the temperature on Venus. We'll talk about Earth, of course, for the rest of the class. But the other one, Mars. Now, this is my favorite planet, Mars, the great red planet. And the reason why it's my favorite planet, this is the source of Martians. This is where all the space people came from. This is an interesting story. The first person to actually observe any of the planets, including the moon and all, up close and personal,